cyclohexane exists as chair and boat forms. We are asked to draw the conformations and explain why the chair form is more stable. First, we draw the conformations of the chair and boat. In the chair form, we have marked the carbons as 1, 2, 3, 4, 5, 6, and we find 6 carbon-hydrogen bonds are vertical and the other 6 carbon-hydrogen bonds are almost horizontal. They are referred to as axial and equatorial bonds respectively. We are given A for axial and E for equatorial. The equatorial bonds are parallel to a pair of carbon-carbon bonds. For example, you find carbon 5,6, carbon 2,3, they form 2 parallel covalent bonds. In carbon 1, we have marked an equatorial bond which is parallel to the bond 6,5 and 2,3. So, we have 6 axial bonds and 6 equatorial bonds. Generally, the equatorial bond is preferred by bulkier groups. We find alternately the axial bonds are pointing down or vertically up. Alternately, we find on carbon 1 the bond is going vertically downwards. On carbon 2, we find the axial bond is vertically upwards. If the axial bond points downwards, the equatorial would point upwards with respect to the plane of the chair. Similarly, we have drawn the boat form. Now, to explain the stability, we have to show that the chair form is staggered and the boat form is the eclipsed form of cyclohexane. The Newman projection can be drawn by looking through the face formed by carbons 2, 1, 6. Carbon 5 and carbon 3 get eclipsed behind carbon 6 and 2 respectively. We see carbon 1 coming below and carbon 4 going upwards. This shows the chair form is the staggered form. Repeating this for the boat form, looking through the face formed by 1, 2, 6, we find the eclipsed form is the boat form. As we know, the staggered form is more stable and therefore the chair form is more stable.